Today I'm going to talk about not the dislocation plasticity, but microfracture behavior of powder coatings. So before we start, I would like to mention that most of the work is the PhD thesis of one of PhD student Micro in Zhang. So what's the hard coatings? It is special type of material which can protect some substrate or some soft materials from the degradation. For example, we are using this material for protecting some tool steels. I think you can understand the applications. Like we put them we put very thin coating layer on steel so that we can use it for drill bit or even a larger construction, so that we can have more larger lifetime of the material. And typical type of hard coatings are either nitride or carbide and chloride the coatings. They have very high hardness, as you can guess from their name. However, the limiting factor or they have some problem with the fracture toughness of the fracture toughness. So usually they have very low fracture toughness, which means they fracture, but they are very brittle. So this is the one of the limiting factors which limit their applications. So people have tried to improve their fracture toughness by very different methods. For example, one of the most popular approach or way is that introducing interfaces inside the material. For example, they put some phase boundaries or tune boundaries or some other grain boundaries so that crack can deflect or we can trigger crack to consume more energy or absorb more energy, which can improve the fracture toughness. Or people have tried to introduce some secondary phases, which will be transformed to another phase, which will, of course, absorb more energy, so they can improve the fracture toughness. Or introducing some residual stress inside coating is also one of the very popular approach to improve the fracture toughness. If you can imagine some kind of some steel, and then the hard coating concept is we put some material on top, and people, as I said, people try to improve the fracture toughness of the entire system by these approaches. However, I mean, from our very basic material science lectures, we all know that the fracture is starting from flaws or some defect inside the materials. So if there's such a small defect inside the fracture inside hard coating, then the fracture will happen here. So what I want to say in this slide is that instead of focusing on how to improve the fracture toughness of the material, we need to understand what is the weakest point, or what is the weakest link of the material. And then, as I said before, from the Griffith theory, we all know that such a crack or micro cracks or some defect inside material will be weakest link, and then we need to focus on finding this weakest link inside samples. And actually, we may already know the answer. What are the weakest points in our material system, especially in the hard coatings? When we break the sample, just bending it or fracture it, then we can very nicely see the microstructure of those hard coatings, typically fabricated by PVD technique. And as you can see, all these SEM images, they usually have such a columnar grain structures with the grain size of a few tens of nanometers. It's very nice to see their microstructure very easily. However, we can already see that or guess that the grain boundaries are can be the weakest point, because they just fracture along the grain boundaries, not by the transgranular fracture behavior. So this is the point we and my team wanted to study. So the scientific question we had in this project was that whether we can quantify the effects of the grain boundaries in the fracture toughness of hard coatings. And as you saw in the previous SEM images, they usually have a very nice texture. The columnar grain bond, they usually grow in a columnar grain structure. And our second question was whether there's any influence of the loading direction on the fracture toughness. And lastly, we wanted to see what happens at the more extreme conditions, for example, high temperature. So these are the samples we tested. We used three. I'm showing here 2 samples, but there's one more. But we prepared 3 different samples. One of them is a monolithic sample, which means it's either monolithic chromium nitride or aluminum nitride coating. And we prepared by using PVD processes. And we grown them on either on silicon substrate or NGO substrate. And the second sample is the chromium nitride and aluminum nitride spolated structure, or it's a multi-layer structure with a layer spacing of 4 nanometers and 2 nanometers. And all of them show such a very nice columnar grain structure. And these are the fifth ion channeling image, which shows the columnar grain structure, and this is top view image, shows the grain size, which is around a few tenths of 20 to 30 nanometers. And the last set of sample is something special. I would call it hybrid structured hard coating, because when we grown this multi-layer structure on NGO substrate, due to the very small misfit strain, they initially start to grow in an epithelial structure without grain boundaries. And at a certain point, the columnar grain structure pops up. So as you can see in the TM image, this is the NGO substrate, and there's the epithelial layer, and on top of it, there's a polycrystalline or columnar grain structure. And this stem HDF image and EDS images show that the multi-layer of chromium nitride and aluminum nitride layers, which are alternating. And the total thickness of the samples were around 1.8 to 2 micrometers. So then we prepared micro cantilevers using focused ion beam, and they look like this.